Hi everyone, welcome to our event. This event is brought to you by Data Talks Club, which is a community of people who love data. We have weekly events. This is one of such events. If you want to find out more about the events we have, there is a link in the description. Click on this link and you'll find out more about the events we have. We have quite a few lined up. So for example, on this Friday, we will talk about data mesh. If you're interested in learning what it is, I must admit, I have no idea what data mesh is, even though this thing has been around for a couple of years. Finally, I hope I will be able to learn this. Anyways, if you haven't subscribed to our YouTube channel, please do this. You will not regret. You will get notified about all the awesome content we have on this channel. And we have a great Slack community if you want to hang out with other data people. Check it out. During today's presentation, you can ask any question you want, and we will cover these questions at the end of the presentation. And with that, I stop sharing my screen, and the floor is yours.
All right, I'll try to get sharing set up here on the second screen, make sure I'm doing this right. Hopefully you can see that big YLogs logo there. Okay, hello, my name is Jamie. Thanks for having me to present and chat with you guys at Data Talks Club. I'm going to tell you a little bit about my experience of working on design changes that led to a major version bump of the open source project YLogs. While the focus of this talk isn't on the library itself, it's helpful to know a little bit of context about the library. So YLogs is an open source Python library used by data scientists and engineers to profile data and help people monitor machine learning in production. About a year ago, or a little less than a year ago, I started working on this project, and we had a number of requests around making YLogs easier to use, and had requests to have more control over turning on and off different kinds of telemetry and metrics. So these are kind of like normal things you get in a software project after about a couple of years of use, and you start to prioritize features. My goal wasn't really to focus on performance. Really, this was about improving usability, trying to get a few more features in. And one of the strengths of this V0 of the library was that it did a lot of things automatically. So it didn't require users to predefine configuration. It tried to make smart guesses about what kinds of statistics you would want, which led to a little bit of a kitchen sink in its logic. So I approached this project thinking like, how can I improve it? And it looked like it needed a bunch of just structural changes to make it easier to maintain, easier to support some of these new features. So I started off in a place where I was really just focused on like just standard software engineering kind of things, not so much performance. I like to remind myself that if I'm having a lot of fun as a software engineer, it's probably a good indication I'm doing something wrong. If I'm like, oh, I could write my own like cryptography. No, don't do that. If I'm spending a lot of time deep into the performance optimization, a little red flag, it goes off in the back of my mind that says, should I be doing this? And so this is one of the few times where I kind of stumbled into doing a little bit of it, and it came out well. I think like premature optimization, is the root of all evil, is the quote. But there's still that like 3% of the time where it does make sense to spend some time optimizing. So this is just a little bit of the context. And so the design goals were really around usability. We wanted to simplify API calling for people just starting, making it more modular. There's a few features in there, but mostly just around making this easier to use. So this was kind of our first thought, was like, start from the left-hand side. Can we reduce a few lines of code? So before, there's just a little bit of like create a thing to get a thing to then log, and then it's more just static function. We also tried to reduce the set of dependencies that we use just as a means of making it easier to install this tool. And one thing we didn't let go of was NumPy and Pandas. So just as more context, we kind of embraced Pandas, said the thing that we'll do well is try to handle Pandas data frames. So if you know how to do those kind of operations, then we can help you profile that data. What do you get from a YLogs profile is some statistics, and these summaries of your data are rather small compared to input size. And just like, what can you do with it? You can visualize them. People use it to like look at distribution drifts. This is my favorite one here at the bottom. Is we use a KLL sketch from Apache Data Sketches. And from that, it's a rather compact representation of a distribution that we can then compare changes in your data over time, things like that. So although I think usability was the main goal of this project, at some point, performance becomes a usability blocker. We got some feedback from the community that in some scenarios, this was just a little too slow to use. And while the approach of YLogs was to build upon Apache data sketches, this class of online algorithms, which are very good at having very small, compact memory footprint, means we could scale really well. We could scale out on a cluster. So just as an example, like a 100 gig file gives you less than a megabyte of profile on it. And you can still ask a lot of questions. You can validate constraints and different things with that profile. But if it takes too much time to build that profile, it can still be a problem. In batch processing, maybe it's not as much of an issue until you start thinking about like, well, how frequently you're running your batch. You want to make sure that you're still able to produce the profiles in the same cadence. So V0 of the library was great in smaller data sets. Maybe typical kinds of training data sets were still fine. But if you're sitting in a notebook environment and you're waiting for, say, 2,000 input elements to be profiled, it was still taking more than 10 seconds. So we could handle about 15K elements per second, which sounds great until you start looking at, I mean, maybe it doesn't sound great, but to me, it sounded okay until I started looking at some reasonable toy data sets, and it just was, a little bit more time than compared to maybe other libraries or what I expected. So that's kind of the backdrop about why we considered performance to be one of the things we would want to revisit in this major version 1. I talked to Andy Dang, who's one of the founders of YLogs, and a little bit about different ways, longer term, like how could we improve performance? And the thoughts were, well, this is a Python library, so maybe do less work in Python, reuse other libraries, and then this idea of trying to move more of the code or more of the logic into a native layer sounded like a great idea, but also maybe a longer term thing that we weren't going to touch in this major version. So we said, okay, that sounds like we have a kind of plan that we can invest in later, and we'll try to just marginally improve it. So I wrote an experimental PR a couple months ago just to give users configurability so they wouldn't track all the statistics on every single data type. So for example, we used to try to parse and coerce strings into numeric types, and then we would apply every single kind of statistics we knew on each element, whether or not it even made sense. And then it was up to each metric implementation to decide if it was going to handle that input or not. And just removing some of the extraneous computation, we were able to get this down a bit. So this isn't like the final results. This was our checkpoint. I created an experimental PR, gave it to some early adopters, and said, hey, here's the kinds of changes we're looking at for our version font. And it has configurability of metrics. It had customization. So there's a little bit more of the features in there that people asked for. And it looked generally good from an API perspective, but it still was a bit slow. Especially in this bottom row, that's like the roughly a little under 100 gigabytes. It's great to get out of days because it's finally usable in a batch processing system, but 40 minutes still was a bit surprisingly long. So I then decided, okay, this makes sense to dig a little bit deeper. Maybe this is one of those 3% scenarios where it makes sense to try to figure out what's going on with performance. So I'm not a performance expert, but I like these kinds of challenging problems. So this isn't like, any kind of fancy approach here. This is sort of just starting off with some questions. Here's the kinds of things that I tried to ask myself, and then, following a scientific method, try to run some experiments and observations to see how we could improve performance. So, the first thing is, what do things cost? So I profiled the code. I used the C profile and looked at some of the call stacks, which we can dive into. And I was hoping that there would be some outlier, like maybe there was one method that was just really slow, and then you could remove that or optimize it. That's a fairly easy one. Another one that people kind of throw out when they're talking about performance is like, are you using the machine resources well? But in our case, we are a library that profiles your data processing. So I don't want to start spinning up multi-processing. I want the users to do that. And I just want to in the pipeline of your processing, add on a little bit of extra work to profile the input. So if you want to do multi-processing, you can do that on a cluster. Or you could, I mean, in Python, it's also kind of, a lot of people just run this as a single threaded thing. The other kind of thought I had is just like, can you restructure the code for better performance? Like, are there different ways of iterating through the data? Like earlier I said we operate on pandas profiles. I'm sorry, on pandas data frames to create the YLOGS profiles. So like, could we maybe like iterate over the columns versus the rows, or just revisiting that logic, because it was written by some smart people, but they're scientists. So like maybe software engineering made sense to revisit there. And then the other thing I said before was that we tried to calculate every different kind of metric on each element. So just doing a little bit more selective computation, maybe there's some areas where we could skip calculations that weren't needed, that were redundant or early exit. Those are just like, but anyway, all this class of things I thought was probably maybe like I could get 2x out of it. Not a huge amount of performance gain, and not something that's worth like a large investment yet. Maybe the better kind of thinking on this is just like, has someone else already solved my problem, and look for other tools or libraries that do the same kind of tasks well. And like, I think a good example of that is if you look at NumPy or Pandas itself, they have these functions on a column. You can ask like, what is the sum, or what's the variance on a column? And those are pretty fast if you compare it to iterating over each element and calculating yourself with a running algorithm, which is kind of what our V0 approach did. So that turns out to be an important element. All of these actually were used to some degree in tricks that we kind of stumbled upon. I'm gonna just take a pause right here to see if there's any questions yet, just on kind of laying the context of the story.
Yeah, there is a question about Apache data sketches. I don't know, it's not super on topic to this particular slide, but you talked
Sure.
a bit about them. And the question is, how did you land on Apache data sketches, and did you consider any other alternatives? And what is it, by the way? Maybe you can tell us a few words, like what kind of data sketches what kind of data structures you used from there?
Sure. So Apache data sketches are really interesting. I love them. It's like, from a technical perspective, it's a class of algorithms that are written to be like streaming and online. So sketching as a technique gives you probabilistic approximate answers to things. And it can, like, some of the most useful sketches that we use are a cardinality sketch. So it can tell you how many items are unique in a very large data stream. Let's say there's more than 4 billion. You start to need new approaches to say like, well, counting the unique items there isn't really feasible. So this is a nice compact way of giving you an estimate. And that's the hyperlog log we use as the Apache data sketch there. We use the KLL, which is 3 names. I forget the one for a distribution. That's Apache data sketch. We use some of the other sketches. Those are the 2 like most interesting ones for us. There's also some frequent item sketches that gives you like keeps a running list of the top strings you've seen or top items. A lot of these use some fancy math and hashing to give you well understood bounds on the errors. And it's usually a trade-off in the memory input size of the sketch versus the accuracy. In our case, we're trying to do monitoring, so we're not really so much concerned with like the last 0.5% of accuracy on calculating like the means or quantile. So distribution can give you quantiles. So you can say, out of this numerical data, what's the 99th percentile? Or you can actually, it's cool because it encodes a probability mass function. So you can ask for an arbitrary quantile. It's the nice thing about this after the fact. I highly recommend, I'll probably maybe give some links to Apache data sketches. The KLL sketch is really cool. It's something that we at YLOGS, on the project YLOGS, we forked the Apache data sketches library just to add a few things that we needed to make it easier to call for Python. But it's an open source project that you can check out.
Is it C++ or what is it written in?
So Apache data sketches has a couple different. We forked both the Java and the C++. So those are the 2 that we use in YLOGS. I think the question about did we consider other options is a good one. It's actually it predates my tenure here at YLabs. I think it's a very core thing to like, we started with choosing the approach and then built the tool around it. So like, Apache data sketches is core to YLOGS. It's how we summarize large amounts of data into a compact representation. But yeah, it's a good question, and it's worth looking into the benefits of Apache data sketches if you're interested.
And then you wrote a Python wrapper yourself, right?
So there's actually a little Python wrapper. So the C++
it's already there.
fork has PyBind 11 and a small wrapper there. Actually, like right before this, I was working on fixing some stuff there that I messed up in our own port. So yeah, I can also talk about that more. And that's turns out to be, not to give away like a few slides later, but that's turns out to be one of the keys into how we achieved kind of accidentally this large performance gain, was being smarter about how we interface with that library.
Okay, I'm looking forward to seeing that slide.
Yeah, okay. So this is just kind of context. So I use the C profiler in Python, and I find these tables to be fairly useful when I'm first starting out. I used toy data set because I'm impatient and I don't like waiting more than a few seconds. So this is my ylogs v0 profile, and while this didn't give me the answer, it just sort of showed that one of the top things is it's almost all code that's in ylogs itself. So like we are doing the calculation ourselves, and one of the things that was kind of expensive was a lot of this sanitization of the inputs, trying to infer the type of the data and checking for nulls, and then trying to parse it. So these last 3 lines, although they're not a lot of total time, I think the important thing here is the number of calls. Like we have 800,000, and our input size is 10,000 by 20. So like we're doing this 8x for each element. So that's kind of why I was saying, like we had maybe 4 different statistics that we're trying to calculate on every element, and we're just calling like update sketch 1, update sketch 2, update sketch 3, update sketch 4. And before we do that, we're doing a little pre-processing. So there's some redundant calculation there, and there's also like, if we know the data type is an integer, we don't have to do some of these null checks or string parsing magic. Like it's already done for us. Upstream it would be a nice, so we never made those kinds of assumptions in V0. We kind of were appropriately paranoid about our input data and inspected it each time, but it had costs. So to compare it, okay, yeah, I guess the next thing is the flame graphs. Like this to me is kind of where I start having fun when I'm profiling data and trying to figure out where time is spent. Again, like I looked at this, and there's a lot of this like calls for track, which is what we do. So the verb that we use for each statistic is we track some input and we update the Apache data sketch with update. And there's a bunch of like null checks. This is roughly 7 seconds of time. It's all focused on this log data frame call here at the bottom there. And like I looked at this and nothing really jumped out at me other than like maybe we can, again, like I said before, maybe we can reduce some of the unnecessary computation. Maybe we can just be a little bit more efficient. But I was thinking like, unless we do a design change, we're not gonna, or we vectorize things more, like moving things into C++ calculation from Python, which is a bigger change than we wanted to do for this version bump, then we weren't gonna see more than maybe like a 2x performance improvement. Here's ylogs v1. Oh yeah,
question. Sorry, like how did you build this flame graph? It looks
sure. So yeah, so this is so I used to use this a lot in like profiling C++ applications in my previous job, where performance also was important. But so this is just using the C profile part of Python, and then that outputs I wrote the stats to a file. So the previous slide, maybe this is something that people are familiar with. This is actually what the tool produces first, is just the output. And then you can also output to a file. And I used FlameProf, just a tool that lets you create the flame chart from that file. We could put links to that too.
So if I want to find it, so I just go to Google and type in something like
pip install FlameProf. Yeah, or C profile is like, the C profile is the really more common thing, and then I just took some random tool that I found that did the job.
Okay, thank you.
Flame graph. Right. So I guess this is kind of giving away the answer. I don't know if anyone can see. This is a C profiler output, the top 10 ordered calls by cumulative time from ylogs v1. Now this is on toy data, so it's not actually the 500x, but it's still like 100x faster, or 80 something. I'm curious if anyone notices like what is a really big difference here. I don't know if there's some delay in the questions here, but
yeah, there is I don't know, 10, 15 seconds, which is quite
Oh,
long.
okay. Yeah. So if somebody comes up with it, we can loop back to it. Maybe I could put Alexi, you on the spot here.
Yeah, I can try. So I see that ncalls column is
Yeah.
a few orders of magnitude smaller.
Good
Yes.
observation. That turns out to be the key thing here. So we had a user who had tested out ylogs v0 and noticed that when you profile very large integers, like above what you could represent with a float 16, say like you had an ID column in a database, ylogs v0 didn't really know about the semantics of the data. It just says, hey, this is a numeric data. I'm going to use the KLL sketch on it and the other sketches. If you start profiling like some monotonically increasing ID, well, one, your KLL sketch might not be that useful on it, but also you start getting numerical issues. So in Apache data sketches, the C++ library, it treated the only type of KLL sketch it supported was a C++ float. So there's actually some numerical issues going, you just send from Python float, you're losing half of that precision going down to the KLL C++ float, because they're not, Python float's not the same as the C++ float. So
It probably doesn't make much sense to do a histogram of an ID, right?
right, but we just did it anyway. And so we noticed that actually there was some errors because we started rounding numbers, like the distributions look wrong. I think Alexi might remember this. There was a bug I filed on behalf of a gracious user who had run through this. And so we dug into the Apache data sketches underneath and saw that it's templatized. So you can actually create a wrapper for different types, but there was only the float there. So we said, well, let's use this C++ double. That's probably going to be relatively efficient. And while we were kind of mucking around and fixing that, like broke some things along the way, so it took a while to fix it. But we also noticed that, well, maybe to back up is we had an older fork. So we updated, and there's been some improvements in the Apache data sketches. And one of them was better handling of lists and arrays of data. So from Python, you can pass, instead of a scalar and say, update my running statistics on this, you can pass an array of integers. And I thought, well, let's just, let's give us the new things that are in C++ in our next version of ylog, since we're rebuilding it anyway for this numerical precision issue, and we want doubles. I'll also update to include, instead of just update by scalar, update list, and make sure that the Python wrappers work there. And that's how this number of calls is so much lower. So instead of calling metric.update on each scalar, we pass in the array. And we thought, okay, great, that's going to be more efficient.
Column, right?
Oh, sorry, yes. So the way that ylogs processes things is it's per column. It creates a column profile.
Makes sense.
Yes, and so we don't know what kind of data is in a column. I mean, we trust pandas. If we get a D type that tells us, then we'll use that, but it also could be mixed, it could be objects. So we do a pre-processing step where we split out all of the inputs into arrays by type. So if you had mixed floats and ints and strings, we could make little mini batches of those, which we call, and then pass each mini batch to the appropriate sketch. So this toy data isn't quite big enough to really show some of the gains. You get the bigger gains here when you're starting to talk about more gigabytes of data, but still it's significant here, going from like 7 seconds to less than 1/10 of a second. And this is mostly because it's reduction of the number of calls in Python. I'm still surprised that the speed up was so much, because all the C++ Apache data sketch is doing is iterating over each value of the array and calling update. Like the sketch itself doesn't have a column or update. It's much less calls between the Python world and C++ library. So I think that's the main takeaway here. I guess maybe it's not super.
I just wanted to ask, so in one case, you iterated over this array in Python, and in another case, you iterated over this array in C++, right?
That's right. That's right.
Yeah, I guess that makes a huge difference, right?
That's where the biggest difference was, yes. So there's a combination of having selective computation, which we got about 2x out of, about like not trying to apply each statistic over every single data type, but splitting them first. So there's a pre-processing step. And then this columnar update or update a list is the main thing. And that's really, like, I have to credit Andy for that. Like, he was working on that with me and just kind of wired it up. And then we looked at the time and we were like, oh my gosh, like how did it get that much faster? Like, instead of 10, like, did it even run? It's like, yes. We didn't trust it at first. We said, like, are the statistics actually calculated? Yeah, yes, they were. So this is maybe a little harder to infer, but this is the flame graph of the V1. And I think the thing I wanted to point out is this calculation here, this var and this mean, are no longer Ylox code. This is like asking the NumPy to calculate this for us over an array, which then, like, this is my going back to how do you improve performance? Like, has someone else already solved the problem? So we're using the existing libraries to do most of this calculation where we can. And that, like, this is a full screen, but this is 1/10 of a second, and the other one was like 8 seconds. So that's that pretty flame graph. So yeah, like, just to kind of summarize what we were saying here, like, using pandas and NumPy to perform the type checking rather than doing it ourselves in Python. And by doing the type checking, I mean using dtype or something that's metadata on a column and just applying statistics. So we resolve the set of metrics that we calculate during a pre-processing step, not per item. And then, use NumPy to perform mean and variance calculations, passing arrays to the Apache data sketches over passing the scalar values, lowered that call count by a lot. So, I mean, if we just, like, this is the main thing here from this number one is, like, doing this pre-processing step. We split the pandas series up here, and this, like, highlighted line, this dtype, we just make sure that there's not nulls, and then we pass it in. And then here's NumPy's variance. So that array.mean and array.variance is not Ylogs calculating it. It's just asking the underlying library to do it. That turned out to be where a lot of the time was spent when we saw the previous call graph, but it's just minuscule compared to if you did it yourself, because you're leveraging the smart work of these other more mature projects. And you can see, like, we still have to do some of our own calculation there. We have, algorithms for calculating variance. And if we don't have NumPy, we still have fallback, so it'll still work, just not quite as fast. And then here's the Apache Data Sketch C++ library. You see that this KLL sketch update has an array overload, and this is the main one we used. And you can just see here on lines like 137, 138, 139, we're just iterating over that passed in Python array and then calling sketch update. So, I mean, it's the same code, it's just moving that iteration down. It's not anything amazing, but the results are kind of amazing. So I just, when we stumbled upon that and saw that it was, several orders of magnitude faster, I mean, maybe it's not surprising, it's kind of basic, but it's still pretty exciting when you have a mature project that has that much from a small change.
Did you need to update the code, the wrapper code yourself to be able to use this function, or you just discovered using a listing method? Yeah, please.
Yes. So right. Yeah. Sorry, I had a little bit of a like. So there is an existing method for update with an array, but that was a recent addition to the Apache Data Sketches library, and our previous version that we used didn't have it, so we hadn't looked at it because we're using a rather old version in Ylogs v0. So in Ylogs v1, like I was saying before, we wanted to make sure that we were taking advantage of doubles if possible here, and we wanted to make sure that we were getting any bug fixes, so we updated our fork, and we noticed that this method had been there for a while. We just weren't aware of it. And then we added another wrapper here to make it easier to work with doubles and make it easier to call in Python. So there's just some very small changes we made here. There's actually some bug fixes I'll see if I can push to the main line so we don't have to maintain them in our fork. But so that's the main, like, if anyone's using a C++ library underneath the hood with Python, I mean, this is maybe something obvious to many of you, but doing more of the work, even if it's something like just iterating over arrays, can be a big gain. Like we knew that we didn't want to do the actual sketch calculation in Python, but I think we had overlooked some of this, just like how many times are you calling through from Python to the C++ layer through PyBind was a big big source of our costs.
I guess there is some
Uh,
overhead, right? When you
Yes.
invoke a native method, native function from your Python code, then there is like a bit of overhead, right? And if you can remove this overhead from each call and just send this in batch, then yeah, it effectively removes
Right.
this overhead, right?
Yes, and another thing is like we didn't spend a lot of time even optimizing this. I suspect there's still probably another 2x gain just to make sure that we're passing the array in a smart way without like copying it and stuff like that. But just reducing that overhead turned out to be a huge gain for us. So here is just a side by side on a single machine. This is on my laptop. We had some of this test benchmarks from people in the community who said that it's a little slow for us when we're running these larger data sets. I actually couldn't run this last line on my laptop with V0 because it tries to load the whole data frame and it's almost 100 gigs. And I don't have that much memory. So I had to adapt it and do a columnar update, which worked. And then I was impatient and didn't want to wait 7 days. So I just said, based off the first 10%, it's about 7.1 days. But in V1, we could actually handle it because we're doing columnar updates anyway. As long as you split up your data frame, we can produce a single YLOX profile from that data size. It still takes a bit of time. So think at about 17 minutes it's fine probably for some batch jobs, but it might be useful to get a cluster once you're getting above 100 gigabytes or so. And so in that context, I ran this on a Databricks cluster. So another thing that's kind of cool is YLogs v0 relied on a Java implementation to run on Spark, to run on Apache Spark clusters. And so it was actually kind of a little bit complicated to get set up. So if people are familiar, you have to make sure that your Java jars align with the version of your clusters, Scala and Spark. And there's just a lot of like, if you're just starting out, it's hard to get up and running if you're not familiar with that. So this is a lot better in that we are using just Python in YLogs v1. I mean, we have the Apache data sketches, but the install requirements are just, you can do it with a pip install. And on the Databricks cluster, that's pretty easy. And this seems to just work. There's really cool new PySpark features that let you run native Python functions over iterators of Pandas data frames. So because we kind of embraced Pandas data frames, it was very easy for us to efficiently move over our profiling code to a Databricks cluster. So this is just without me optimizing it, just throwing our existing Python profile function onto a Databricks cluster. And this thing that used to take 7 days is now 2.2 minutes. Those of you out there might realize that, saying how long it takes on the cluster is kind of an arbitrary thing because you could always scale up the cluster. But just to give some details, this was roughly a little over 100 tasks in parallel. I had a dynamic cluster. It was 16 machines instances. I just tried to get some spot instances. I mean, they were big ones that used C5s. But I figured it's worth the price of a latte to run this experiment kind of thing. I wasn't throwing, you could get higher than this, but once you start getting below a minute, you're spending a lot of time on the overhead of resizing the cluster and things like that. So it's kind of hard to actually, I would stop optimizing at that point, just make it cheaper maybe, but don't throw more machines at it. So that's the results there. And yeah, so Map and Pandas was my friend, and PySpark. There's a bunch of new APIs around running UDFs across Spark data frames. And you can take advantage of Apache Arrow to have more memory efficient handling of the Spark data frame to Pandas data frame to our code to C++. So there's still, I noticed when I was digging into this, we still have some inefficiencies there, but it's pretty good. So there's some links there if people are interested in looking at that more. And then we have an example of how to put this together in our YLogs repo, just a profiling notebook that uses Spark. I think that's my content there. Oh no, wait, yeah, Spark did. Yeah, I clicked out. Sorry. So this is just showing you kind of what the call stack is like. If you have a data frame, we have this new collect column profile views or collect dataset profiles. And you just pass in a Spark data frame and it will give you a YLogs profile out. This one here is just showing kind of my last run here on some not toy data set, but it's about 10 gigs. I guess the thing I was trying to highlight here is that we're still doing some like shuffle writes in this experiment. Those are the kinds of things that I would try to reduce, because you don't like the output of this processing is like I said before, it's under a megabyte. Each profile is very small. So if you partition your data well, you shouldn't need to do much shuffling of the data as you're profiling here. And the main thing here is that we're just executing within this map and pandas here. This is just the Spark thing. Yeah, some more Spark stuff. I'll pause to see if there's any more questions.
Yeah, actually there is a question. So any chance you did profiling with Modin versus native pandas or PySpark for data frames? I don't know, Modin, do you know what Modin is? Is it some sort of data frame library?
So I haven't dug into it, so I can't really answer that question, but it is on our list of things to try. So we have kind of a bunch of different other technologies that we want to look at and do some more comparison. Like, this isn't really this is sort of, I would say, an intermediary level into performance. Like, that's maybe like the next level would involve some more comparison of those existing tools. But because, you know, like I started off with this set of redesign focused on usability, we didn't want to invest too much in performance yet, but we kind of accidentally got some.
Okay. And I guess the key thing here, why you could use cluster to speed it up, is because like all these sketches and hence profiles based on these sketches are mergeable, right? So you can build two sketches and then combine them, and it's the same as if you run the whole thing, or like run it on the whole thing, right?
Yes, right.
That's why like it's super, like, how do you call it, embarrassingly parallelizable, right? So you can just throw in as many machines as possible, and then you have one profile at the end, right?
Absolutely, right. So there's some really good talks by like Danny previously on my team, just kind of doing the overview of what YLog's profiles are, because they're based off of Apache data sketches and they're very small. Apache data sketches as a class of algorithms has some representation of statistics, and they are mergeable. Now, they're not the same, they're statistically equivalent kind of thing. So like you might get slightly different, I mean, it updates itself when you merge two profiles, but the output is still within those same error bounds of the probabilistic like trade-off between size and error that you have, whether it's whether you're trying to calculate cardinality with HLL or distributions with the KLL sketch. Yeah, so that's right. In principle, you got it. Yeah.
And you said that you on purpose didn't do any multi-threading and so on. So this is all one-threaded, right? Single core.
Yeah. So like the interesting thing is we're not managing the multi-threading, but in Apache like Spark here, like we are running on a number of different executors.
Yeah, here,
so
it's clear, of course.
So it's right, and I think this kind of right. But I think this illustrates like why we didn't go into the multi-processing, is because there are other tools that do that, and we assume, or it's maybe easier to integrate if you don't have your tool doing the multi-processing as well. If you have a large data set that you need to process, you probably want to start thinking about those techniques when you apply it to your machine learning pipeline or your data processing. And if you can plug in YLog's profiling there, that we want that to work well, without it like spinning up a bunch of extra threads. And, I mean, you know, we could do a little bit of async IO, but we're generally executing and processing the data in process.
Yeah, I remember there was an issue with XGBoost. So XGBoost, like it's very good at utilizing all the cores of your computer.
Yes.
Like 200%.
Yeah.
And if you try to, like, let's say you have a Spark cluster with a bunch of workers, right? And the worker has 8 CPUs. So like it has I don't know, however many executors, and each of these executors is running XGBoost predict, and each of these XGBoost is trying to utilize 100% CPUs, right? And then, yeah, it kills the cluster. So you have to be careful there and, you know, limit XGBoost to only one core. I guess you use the same reasoning here, right?
Yeah, there's a similar, right? It's a similar set of principles there, is that, you know, you might have stability issues. If we were really good at using all the machine resources, you might run into problems. So we're trying not to wade into that approach prematurely, or so the simplest thing for us to do is just to say we're executing in the same process as the calling process for this Python library.
Yeah. Is it something you wanted to talk about on this slide, or I can ask the next question?
No, I think I can ask the next question. I'm pretty much done here with my content, so
Okay.
I don't know if I blew through it fast, but
okay. So there is a question about Python. So how, like, you can probably use Python to optimize some of the code. And did you experiment with this? And in your opinion, how difficult it is to migrate some of the Python code to Python?
Right, it's on our list, and I don't think it's too difficult. And this is probably one of the things we'll do next in the next quarter or so. Is just look at some of those already existing executing Python code efficiently sort of libraries. But because the most interesting calculations are already in a C++ library with Apache data sketches, it was more for us like this easier gain we had by just trying to move some of the stuff. Now, there are things that we calculate as a fallback. So like I said earlier, we don't have very many dependencies. We actually don't even depend on pandas and NumPy. We stub them out. And if they are present, we execute much more efficiently. So the Python kind of approach would be really maybe useful when we don't have NumPy or pandas and we're doing that fallback calculation. We could have a more efficient execution. So that's probably a good medium investment to getting some significant gains there, but it's still not the most common scenario for us. Most of our users are coming from they're data scientists or engineers that are using pandas and NumPy, and those are present in most environments that people use. So the performance gains there wouldn't be zero, but it wouldn't be orders of magnitude either. For the common scenario. Now, for the fallback, yes, that's probably right. But we didn't run the experiments yet. I just kind of looked at it and said, yeah, that looks great. Let's do it next. The other thing that's maybe even a bigger investment, we're like, oh, wouldn't it be cool to just write this whole thing in C++ since we saw such big performance gains? But also, it's a tool that's going to be used by a large number of people. So we make sure that it still probably makes sense to have a Python API wrapper around it. So maybe we just make the PyBind 11 approach and just move more of the YLOX calculation into C++ or Rust, or take your pick of fun programming languages. I'm pretty excited about that, but that's a bigger engineering effort. So I try to keep this small so we didn't disrupt too much. And I think Python makes sense as the next step. And there's a couple other technologies that we'll need to do some experiments with as well.
What are these technologies?
We didn't use we didn't look at PyPy or there's a bunch of other things that just there's different ways of executing Python efficiently, and sort of made a list. I'm not an expert in that area, so that probably won't go into what makes sense to do, and I'm open to suggestions there. But we made a list and we'll run some experiments.
There is a library called Numba. I don't know how to pronounce it. Numba. I don't know if it actually makes sense to use this for a library. This is usually you would probably use it for your code as a user, but then it adds, I guess, an extra dependency, and then I don't know how exactly this just-in-time compilation will work. Does it have any surprises? But in my experience as a user, as a data scientist, there is a very easy way to speed up my code. It's just add an annotation from Numba, and then it just magically has 5x speed up. Especially when it's number crunching, then it can easily be more than 5x, 10x, 20x. Nice. Yeah. So for anyone who's listening, Numba is a really one of my favorite libraries, Python libraries. It's just so easy. Just add an annotation, compile it, and no need to do this Python magic, because in Python you still need to compile this, right?
Yeah. So I mean, even in our the C++ Apache data sketches is the source of some of our limitations around which different instruction set architectures we can run on. We didn't build it for the Mac M1 ARMs right away, so there's a lot of people getting new machines at their new jobs, and rightfully so wanted it to work, and we're sorry, we have to rebuild that, because once you start going lower level, you have to manage some of those things too that maybe we didn't have to do if we weren't using the C++ builds. Yeah, so there's a trade-off there for sure.
And then ARM doesn't only exist on Macs and Linux.
Yes.
There is also Windows. So, for example, I have a tablet, it's Microsoft Surface, but
Nice,
nobody cares about ARM64 for Windows. It's virtually impossible to get anything. So if I want to do something, I have to compile myself, and then good luck. At least with Macs now, they're getting wider adoption, this M1 thing. So there are libraries compiled to this, but with ARM.
I know. Yeah, when we first started, like in V0, we had some of ylogs. We have a number of different dependencies, and when I looked at some of our dependencies hadn't support M1, I was like, okay, I can wait. We'll wait till the ecosystem gets the support there, and then we can fix that. So there's definitely
better, right?
It is, yeah. It looks much better. So I mean, in terms of like other things we could do to speed up, I mean, I also didn't talk like we're not like integrating with GPU cores or different things like that. Like there's also other like as you increase complexity and try to take advantage of different kinds of hardware, you can get really big performance gains, but it comes at a cost, and we're kind of small. So trying to choose the things we invest in very carefully. And like I said earlier, performance wasn't a primary goal of what we were investing. We were just trying to make it more usable and maybe a little bit faster. So
yeah,
that was my hidden gem.
Yeah, I just stopped sharing your screen. Sorry.
Oh yeah, thank you. Sorry. Yes.
Maybe people will enjoy looking at our faces rather than Spark diagram.
Yeah,
there are a couple of questions. I don't know.
Sure.
Like they are relevant to this discussion, but one of the questions from Evan is, can we integrate this library ylogs with GeoPandas to work with spatial datasets? Is it a use case you observed?
That's a really cool idea. I haven't tested it, so I don't know. But I mean, you can try, and if I guess it depends on like what kind of statistics are you calculating. A lot of our core scenarios are in ylogs are trying to go after just tabular data first, and then we have a list of things that we handle to some extent that we're on a roadmap, like more structured data, handling like images and video, NLP. Those are all things that we have some starts to. Geospatial, we haven't dug into yet, so I no promises that anything is really meaningful there, but if you have numerical data, we can give you statistical profiles on that, so that might be useful still, even if we don't understand like GPS coordinates or whatever you're profiling.
I'm just curious.
Profiling the metadata is sometimes helpful.
Yeah, I just started thinking about use cases, so I think it's pretty cool to get some statistics first, like, I don't know, on a district level, then you kind of zoom out, and then you get statistics on the city level, then, I don't know, level.
So this is a really cool thing about mergeable profiles, because like we said earlier, embarrassingly parallelizable, because our calculations are all independent. You can also do really cool roll-ups. So if you have fine granular data and you segment your data by some region, you could so this isn't geospatial data, but like, let's say you were segmenting your data across some large geographic zone. If you just said, I want to process batches of these, and you preserve those profiles, you could merge them, because merge is very, very efficient, and the profiles are pretty small. So even if you had 1,000 profiles, it's still reasonable. And then you could do those kinds of analysis, like you said, Alexei, like tell me what the distribution is over some region of the world, and then go down to the finest granularity you get. But there's a trade-off there, because the number of profiles increases linearly. Increases linearly the size requirements of storing those profiles. Maybe that's obvious.
Another question, I think we're kind of late with this, with answering it. I think it was answered somewhere in the middle of the presentation. So the question was, is ylogs open source?
Yes. Yes. Yeah. So ylogs is open source. It should stand on its own. Like I'm one of the main maintainers there, and we are committed to making it usable without using ylabs. I think the thing that is related there is that we produce these statistical profiles of your data, and it's useful to understand your data, but it's also maybe hard to do this periodic monitoring over time. So if you want to understand if your models in production, your ML models in production are breaking, it may be useful to look for like distribution drifts and things like that. So that's the core scenario that ylogs was motivated by.
So in summary, you can use ylogs on your own independently, but if you
Yes.
want to get some extra functionality on top of that, some how do you call it, software as a service to detect
Yes.
extra things,
Yes.
then you go with ylabs, right?
Yeah, I mean, if you have this time series of profiles, it becomes a non-trivial task to manage those. So that's what YLabs does, is you can send the profiles over to us and we will store them and then perform some fancy monitoring on it to tell you things beyond maybe what's obvious from eyeballing two different distributions and seeing what drift there. I mean, we're pretty good at that eyeballing, but you know, if you want something that scales and is automated, you can use our service there too. Or build your own. I like both scenarios. So.
Okay. Yeah, it's much more fun to build our own stuff, right? Rather than
Yes, I mean that's
rather
why I'm
than
here.
exactly. Yeah, there is actually I wanted to ask you something from the very beginning. So at the beginning you
Oh yes.
mentioned about telemetry, right? I think it was like one of the first slides, and I wanted to ask you. So what do you actually track? Like, do you also track in ylogs? Do you track how much time it takes to invoke certain functions? Like, did
That's
you
it.
observe
Yeah.
this, like that it takes some time for some of the data frames?
So we don't in a customer or like in a user's installation of Ylox, we don't track that the performance, the runtime performance of it. It's a really good insight that our statistical profiles would be a concise way of gathering that kind of telemetry. So it's something that we talked about and like we can use our KLL sketch to just like for call times to see how fast it is and if we collected metadata about platform that may be really interesting. Um,
Okay, so
haven't
I
done that
think I
yet, but we talked
misunderstood,
about it.
right?
Yeah.
So what you mean, what you want to say now is that you can use ylogs for telemetry, but
Yes.
you
Sorry. Yes. Yes.
okay.
Yes.
I thought like at the beginning I was a bit confused, like why are you bringing this up? I thought like you collected some
Sorry.
data from users and okay.
Right. No,
Mm,
I'm just saying conceptually, like the class of things that you
yeah, got it, got it.
collect.
Yeah. Yeah, we have another question is
Okay.
so YLabs is about observability. Do you have any plans for explainability?
So I think I'll defer those questions to my smart marketing guys and more of the leadership of YLabs, since I'm pretty much just like focused on solving the problems. That sounds interesting, but yeah, I'll
Yeah.
defer that to.
Yeah,
That's a question for like Danny or yeah.
yeah. So we have Danny in Slack. So just
Okay, good.
ask.
Yeah, yeah.
Yeah, you can ask your question there. So he'll be very happy to answer. I don't see any other questions. So
Okay.
let me check. No, I think we covered everything. So I guess the summary of your talk is vectorize. Let's use this vectorized
Yes.
things, delegate to NumPy, delegate to pandas as much as possible, vectorize, and if it's possible to have the for loop in your native code, then do it there instead of in Python, right?
Yeah,
That's
and
the
measure. Like, look at what your
measure.
code's doing first. Yeah,
Yeah, it would
they're
be
all obvious
silly.
things.
Yeah, it would be silly, right? You first optimize and then after that do benchmarks, right? It should be the other way
Right,
around.
right. Yes, yes.
Okay, that's
Cool.
it for today, I guess. Thanks a lot for joining us today, for sharing
Yeah,
this experience with us. And yeah, thanks
yeah.
everyone
Thanks for having
also
me
for
on.
joining us and asking questions and watching it. Yeah, so I guess that's it. Everyone
Great.
have a great day.